Okay, section 4.3, and it might be section 4.2 in some older versions of Anton, is about spanning sets. So let V be a vector space, and you can think of it as just Rn. And here's the definition of a span. So let V1 to Vr be some vectors or elements of this vector space V. We say that V1 up through Vr span V if every vector W in their vector space is a linear combination of those given vectors. So again, linear combination means that W can be written as some combination C1v1 plus C2v2 plus on and on CRVR for some scalars or numbers C1 through CR that depend on W. So here's an example. The standard basis vectors E1 through En, those are the vectors that have 1 in exactly one spot, 0 elsewhere. So these standard basis vectors span Rn. Since for any vector W with components W1 up to Wn in Rn, well, now we're going to start writing these vectors as column vectors. Like so, this is an n by 1 column vector. Anyway, W is this linear combination of the standard basis vectors. We've seen this before, but let me just run through the simple calculation again. W1 times the standard basis vector, E1. Now again, I'm writing it as a column vector, which is what we're going to start doing more frequently. W1 times E1 plus so on Wn up to En. So remember, En is 0, 0, 0, ending at a 1. And okay, W1 times this column vector is W1 in the first spot, 0s elsewhere, and so on. Wn times this column vector is Wn times 0, Wn times 0, and finally ending with Wn times 1, which is Wn. And then when you add up all these together, well, W1 only occurs in the first row, and likewise W2, which I haven't shown, occurs in the second row, and so on, and Wn will occur in the last row. So we get, indeed, that W is equal to this sum on the right. We're going to be able to express these linear combinations as a product of a matrix times that coefficient vector C1 up to Cn, as follows. So let V1 up to Vr be our vectors. Write them as column vectors. And so, for example, if V1 is given as a vector with components A1 up to An as an n-tuple, then write V1 as a column vector like so, and form the n by R matrix A, whose columns are V1 up through Vr. So A is, the first column is V1, written vertically. These things here are not ones, but just vertical dashes. Then the second column of A is V2, and so forth. So this is going to be a key shortcut to remember. Form this matrix A whose columns are V1 up through Vn, not the rows, even though typically or often vectors will be given as rows, but you want to convert those rows into columns and put them into this matrix A, and we'll see why we're doing this on the next slide. So the reason we're doing it this way is then that the linear combination C1v1 up to CRVR, when expressed as a column vector, is this matrix product, A times C1 down to CR, expressed as an R by 1 column vector. And why is that? Well, okay, so we've got C1 to CR times V1, C1 times V1, and so forth. Now, when we do this matrix multiplication, so here's our matrix A, here's our column vector, then C1, you're multiplying this row V1 in each spot when you do the matrix multiplication. And so if you think about it, that's the same as taking C1 and multiplying the vector V1. Again, when you multiply a scalar by a matrix, you multiply each component of the matrix. And then similarly, you're adding up to all these terms and ending with CR times the vector VR written as a column vector. Let's do an example. Suppose we're given vectors V1, V2, and V3 in R4. So they're given as 4 tuples written, horizontally, if you will. And then the exercise is to express the linear combination C1, V1, C2, V2, and C3, V3 as a column vector. So the first step of the solution is to form the matrix A, whose columns, and again, let me emphasize, the columns are v1, v2, and v3 as column vectors. So 1, 5, 0, 1, I've written that now vertically. 3, 2, negative 1, 0, also written vertically, and so forth with v3. And then I take this matrix A, and in the second step, I multiply by this 3 by 1 column vector containing the coefficients, and then do the matrix multiplication. So I've got this row 1, 3, 7 dotted with this column vector here, gives me C1 plus 3C2 plus 7C3, and so on. So I'm taking a 4 by 3 matrix, multiplying it by a 3 by 1, and so the answer is going to be a 4 by 1, 4 rows, 1 column. So this is a single column vector, and that's, again, what I'm expecting. And then similarly, doing the rest of the matrix multiplication, you get this answer. So this is the final answer. Now, just to compare it with what we would do if we wrote out everything horizontally, so C1, V1, well, C1 and V1 written horizontally is like this, likewise for C2, V2, and so forth. And then when we multiplied C1 by this vector, we'd multiply each component, likewise for C2 and C3, and then when we added these three vectors, we'd add the corresponding components to get this, this, and so forth. And now you can compare this way is the first component is C1 plus C3C2 plus 7C3. That's exactly the answer we got here. And so they're both correct ways to do this problem, but because matrix multiplication is a bit more useful theoretically, we're going to start switching to this column notation for expressing vectors. Okay, here's an example from Anton, page 201, number 11a, and it says, determine if the following vectors in R3 span R3. So we've given these three vectors, and again, the definition of span is asking, can every vector in R3 be written as a linear combination of these three vectors? So, okay, to start working on this problem, okay, we have to take an arbitrary vector. An arbitrary vector in R3 has components b1, b2, b3. I chose some variable b. I could choose, of course, any variable. And so this question is equivalent to solving the following matrix equation. We have formed our matrix A out of the vectors here. Again, the columns of A are these vectors written as column vectors. So 2, 2, 2, here's this column 2, 2, 2, and so on. And we're trying to find numbers C1, C2, and C3 that equal some other unknown or arbitrary numbers b1, b2, b3. So again, here's this equation in maybe more compact form for this vector A. And then we can solve this equation if A has an inverse, because then the answer for what C is A inverse times B. So the idea is we simply have to check if A has an inverse. We don't need to do anything with the vector B. And a square matrix is invertible if and only if its determinant is non-zero. So all we have to do is compute the determinant of A. Here's how to compute the determinant. We can do expansion by minors along the first row, especially considering there's some zeros. So the determinant of A is 2 times this matrix 0, 1, 3, 1, determinant of that matrix rather, and then followed by negative 0 times the determinant of whatever is left over, 2, 1, 2, 1, but because we're multiplying by 0, I don't really care what that matrix is, and likewise for the last position here, it's 0 times whatever the determinant of this matrix is, but I don't care what that actual value is. Since I'm multiplying by 0, it's going to eventually disappear or turn into 0. Anyway, so doing the algebra, or the arithmetic rather, we get that the determinant is negative 6, and that's non-zero. And so we know that the matrix is invertible, and therefore those original three vectors span R3, is our final answer. Now, we didn't have to choose a concrete value for the vector b1, b2, b3, but let's now, just for the sake of it, choose a specific value. So the fact that these given vectors span R3 means pick any vector in R3. Now, I just chose some random vector 2, minus 2, 4, and it should be a linear combination of these three vectors. In other words, there should be some numbers, C1, C2, and C3, that are going to make this equation true. And to figure out what those numbers are, we just have to row reduce this matrix here. This is the augmented matrix corresponding to the system of equations given by this matrix equation. And then I've done the steps of row reduction here. What did I do? I apparently divided through by 2 in the first row, then turned this 2 into a 0, then turned this 2 into a 0 by adding multiples of row 1, and then swapped, swapped these two rows before that. And anyway, continuing with the row reduction process, we get this as the reduced row echelon form. And so that means that C1 equals 1, C2 equals 2, and C3 equals -4. And of course, we can just check that. So again, this is for that specific value, B1, B2, B3 equals 2, -2, and 4. Now, an observation is that if you have three vectors in R3, they span R3 exactly when the 3 by 3 matrix they form has a non-zero determinant. And this generalizes not just to specific number 3, but any number n. Let's do exercise 19a on page 201. So it says, let T sub A be the transformation from R2 to R2 given by left multiplication by the matrix A, where the matrix A is given by this matrix 1, minus 1, 0, 2. Let U1 and U2 be these two given vectors. Determine if these two vectors, TA of U1, TA of U2, span R2. Okay, so the solution is just compute first what these two vectors are. So T sub A of U1 is matrix multiplication A times U1. I've done the matrix multiplication here. A is a 2 by 2 matrix. U1 is a 2 by 1 matrix. The result is going to be a 2 by 1 matrix. Similarly, I compute TA of U2. And so the question boils down to, do these vectors, minus 1, 4, and minus 2, 2, span R2? And we've just seen that that boils down to throwing them into a matrix and just asking, is the determinant non-zero? I've computed the determinant to be 6, and which is certainly non-zero. And so the answer is yes, they do span R2. In terms of a picture, these two vectors, minus 1, 4 and minus 2, 2, look like so. And they will turn out to, as we've just seen, span R2. What's an example of two vectors that don't span R2? Well, two vectors that point in the same or exactly opposite directions. So -1, 4 and 2, -8. I took this vector and multiplied by the scalar -2. So this became 2, this became -8. And these vectors don't span. Their determinant, when you throw them into a determinant, you get a determinant of 0. And so in general, in R2, any two vectors that are not on the same line will span R2.